Every year, over 2 billion tons of asphalt are produced worldwide. But there's a place where even road pavement is an engineering art. Imagine, in the middle of a desert, under a 120-degree sun, asphalt is born that doesn't melt, doesn't crack, and even reflects light. How do oil residues from a tanker turn into a super modified mixture that withstands sandstorms? And what do the RTA laboratories in Dubai hide? If you watch until the end, you'll find out what they never tell you in promotional brochures. It all begins on the waves of the Persian Gulf, where giant tankers slowly cut through the water's surface, carrying millions of barrels of black gold, crude oil. It travels from Iraq, Saudi Arabia, Kuwait, countries where sand and fire have intertwined in an eternal dance of energy. When a tanker slowly docks at one of the UAE ports, for example, at Jebel Ali, one of the largest man-made ports in the world, an act begins where technology and people work as a single organism. Oil, having just completed a transcontinental journey, is pumped into huge tanks, like into concrete hearts. These tanks, hidden in the industrial landscape, are the beginning of the transformation, where raw material becomes the essence of civilization. Next, it travels underground, in pipelines, like arteries leading to oil refineries. In Jebel Ali or Abu Dhabi, it is met by reactors, distillers, chrome columns, and heating furnaces. There, it is heated to a temperature of over 660 degrees Fahrenheit to separate it into fractions. Light components, gasoline, diesel, kerosene, evaporate first. The heaviest residues, which do not evaporate even at high temperatures, are exactly what will become the basis for asphalt. This residue is called heavy fuel oil or vacuum residue. It is fed into a vacuum column, where the pressure is reduced to a minimum, allowing for the separation of even more light fractions without thermal destruction of the heavy molecules. What remains after vacuum distillation is bitumen, a black, viscous substance that is the basis for asphalt. Bitumen itself is too thick and rigid for use in road construction, especially in desert conditions where temperatures can reach 120 degrees. Therefore, it is modified. In special reactors, it is mixed with polymer additives, plasticizers, stabilizers, and sometimes even rubber crumb. This process is called bitumen modification. The result is a material that has high elasticity, resistance to ultraviolet light, does not soften in the sun, and does not crack at night when the temperature drops sharply. In Dubai, polymer-modified bitumen is mainly used, which meets the standards of the RTA, the Emirates Road Agency. When bitumen completes its transformation in specialized reactors, acquiring elasticity, heat resistance, and the ability to withstand the infernal desert sun, a new stage of its journey begins: delivery to asphalt mixing plants. The modified bitumen from the reactor enters heat-insulated tanks that maintain its temperature at approximately 350 degrees Fahrenheit. In a liquid state, it maintains its homogeneity and readiness for mixing with mineral components. Then, it is pumped by high-pressure pumps into sealed pipelines leading to the plant, or, if the plant is located at a distance, it is poured into tank trucks with special thermal containers. Such tankers are built with a double steel body, with an insulating layer that prevents the bitumen from cooling during transport. The road to the plant is like the roots of a city's circulatory system, where every drop matters. The drivers of such bitumen trucks undergo special training. They must maintain a stable speed, avoid sharp braking, and monitor temperature sensors in real time. If the temperature starts to drop, heating is activated so that the mixture does not lose its properties. At the plant, for example at DxB Asphalt Factory in Dubai Industrial City, the tank truck enters a receiving complex where it is connected to the unloading system via reinforced thermal hoses. At this moment, the bitumen is hot, thick, with a characteristic smell reminiscent of a mixture of rubber and metal. It is pumped into intermediate mixing tanks, where it waits for dosing. From this moment, it becomes part of the recipe, in a formula where the weight, viscosity, and temperature of each component determine the durability of the future road surface. One of the largest is the DxB Asphalt Factory in Dubai Industrial City. There, bitumen is heated to 320 degrees Fahrenheit and mixed with mineral aggregates: gabbro, basalt, quartz, sand. Gabbro is a dark volcanic rock mined in the mountains of Fujairah. It has high density and strength, which makes it an ideal aggregate for road pavement. The stone is crushed into fractions smaller than an inch, sifted through vibrating screens, dried in drum dryers, and fed into a mixer. In the mixer, bitumen and aggregates are combined into a hot mass called hot mix asphalt. The temperature of the mixture is 320 degrees Fahrenheit. It must be homogeneous, without lumps, with a precise ratio of components. For this, automated dosing systems are used, which control the weight of each ingredient. After mixing, the asphalt is fed into silos, where it is stored for no more than 6 hours so as not to lose its properties. From there, it is loaded into dump trucks with thermal insulation, which deliver the material to construction sites. On site, the asphalt is distributed over the surface using asphalt pavers, machines that evenly spread the mixture on the roadbed. Then it is compacted with rollers, first vibrating, then static. In the desert, it is important to achieve maximum density to prevent the penetration of sand and water. Therefore, compaction is carried out in several passes, and the asphalt temperature during paving must be at least 250 degrees Fahrenheit. If it drops, the mixture loses its plasticity, and the road will quickly deteriorate. A feature of Dubai's highways is that they have a multi-layer structure. The lower layer is coarse-grained asphalt, which provides load-bearing capacity. The middle layer is made of modified bitumen, which acts as a shock absorber. The top layer is a thin layer with a polymer coating, which provides grip with the wheels and resistance to abrasion. In some cases, light reflecting minerals are added to reduce surface heating. In the desert, it is important to consider not only temperature, but also dust, wind, and humidity fluctuations. Therefore, asphalt plants in Dubai are equipped with air filtration systems, and the mixtures themselves are tested for resistance to abrasive wear, thermal expansion, and even sandstorms. In the RTA laboratories, each batch of asphalt is checked for viscosity, density, water absorption, and thermal stability. If the indicators do not meet the standards, the material is returned for reprocessing. This process, from a tanker of oil to a finished road, takes several days but requires dozens of control stages. And it is thanks to this that Dubai's highways withstand the load of thousands of cars every day, do not melt under the sun, and do not crack at night. Asphalt here is not just a black mass, but an engineering system that combines oil, stone, polymers, and desert endurance. Over 1 million tons of asphalt are produced annually in Dubai, and this figure is growing along with the expansion of infrastructure. The DxB Asphalt Factory alone has a capacity of 240 tons per hour, which allows for supplying large projects without interruptions. For comparison, an average plant in Europe produces about 150 tons per hour. Interestingly, asphalt is the most recycled material in the US, and over 99% of old pavement is returned to production. In Dubai, recycling is also being actively implemented, especially during the reconstruction of old roads in industrial areas. And from which country are you watching us? Ready to dive into a world where science meets brute force and unremarkable gray stones are transformed into the most crucial ingredients for creating modern civilization? Forget about the delicate manufacturing of microchips. We're heading into the very heart of metallurgy, to a real devil's kitchen where ferroalloys are born. This isn't just casting, it's the taming of the Earth's depths, the roar of thousands of volts, and the creation of the very vitamins, without which any steel would be just a boring and weak piece of iron. This is the story of how ordinary ore is turned into concentrated power, capable of making a bridge unbreakable and a turbine eternal. Steel is the foundation of everything. skyscrapers, ships, cars, even the fork you eat with. But steel on its own, obtained simply from iron ore, is a rather capricious lady. It contains a bunch of unwanted impurities, primarily oxygen, which makes it brittle. And it also lacks character. To give it superpowers, incredible strength, resistance to rust, the ability to withstand hellish temperatures, special ingredients must be added. And this is where our heroes come on stage: ferroalloys. These are, in essence, concentrated cocktails of iron and one or more other elements: manganese, silicon, chromium, vanadium, titanium, and many others. They are like the special forces in the world of metallurgy. First, they act as deoxidizers. Entering liquid steel, they greedily snatch all the excess oxygen from it, purifying it. Second, they act as alloying elements, meaning they dissolve in the steel and permanently change its crystal structure, endowing it with those very desired properties. Ferrochrome makes steel stainless. Ferromanganese makes it strong and wear-resistant, and ferrosilicon helps in purification and improves its magnetic properties. So how are these magical powders created? The process begins with gathering the ingredients for our infernal pie. The main component is, of course, the ore containing the element we need. This could be manganese ore, chromite ores, or ordinary quartzite, which is a source of silicon. The second key ingredient is a reducing agent. Most often, this is coke, coal, or charcoal. Its job is to steal the oxygen from the ore. And the third component is a flux, for example, limestone or dolomite, which helps to gather all the unwanted impurities into a separate, easily separable mass. All this is crushed, mixed in strictly defined proportions, and prepared for shipment to the very heart of production. The process begins with gathering the ingredients for our infernal pie. And this isn't a trip to the supermarket, but a real industrial war with the Earth's crust. The main component is, of course, ore. For the black veins of manganese ore, miners descend into deep, dark labyrinths underground, where the roar of drilling rigs echoes in the eternal night. Chromite ores are mined in similar conditions, or in gigantic quarries that resemble scars on the body of the planet. And ordinary quartzite, the source of silicon, is often mined in quarries where powerful explosions lift thousands of tons of sparkling, sugar-like rock into the air. The second key ingredient is a reducing agent. Most often, this is coke, which is obtained from coal. And coal mining is a spectacle of power. Giant excavators remove entire layers of earth to get to the black as tar deposits, the concentrated sunlight of ancient forests. And the third component is a flux, for example, limestone or dolomite. It is mined in huge, blindingly white quarries that resemble giant amphitheaters. Giant dump trucks, whose wheels are taller than a person, crawl along the terraces, hauling out tons of rock. And the heart of it all is the submerged arc furnace. This is not just a furnace. It's a real monster that hums and roars. A huge cylindrical steel bowl, lined on the inside with a thick layer of refractory brick. And now the most important part. 3 giant carbon electrodes are lowered into this bowl from above. These are not the electrodes in your battery. Each of them can be the size of a telegraph pole and weigh several tons. The prepared mixture of ore, coke, and flux, called the charge, is continuously fed into the furnace, completely submerging the ends of these electrodes. Hence the name submerged arc furnace. A colossal electric voltage is applied to the electrodes. But unlike a steel-making furnace, here the arc does not burn openly. The electric current passes through the charge itself, which resists it, and from this heats up to incredible temperatures, over 3,600 degrees Fahrenheit. Inside this white-hot cauldron, a real chemical battle begins. The coke, heated to the limit, becomes extremely aggressive. It starts to tear away oxygen atoms from the metal oxides contained in the ore. A reduction reaction occurs. For example, manganese oxide plus carbon equals liquid manganese and carbon monoxide. This newly liberated, pure, and very hot metal immediately mixes with the iron, which is also present in the charge, forming that very ferroalloy. All this time, the flux is not idle either. It reacts with the gangue and other impurities, forming a lighter liquid layer, slag, which floats on the surface of the molten metal, protecting it from oxidation. When enough liquid product has accumulated in the furnace, it's time for tapping, the most spectacular moment. A worker, using a special tool, or even a small directed explosion, pierces a hole in the lower part of the furnace, called a tap hole. From there, with a deafening roar and a fountain of dazzling sparks, a stream of white-hot metal erupts. This fiery waterfall is directed into a huge ladle. Since the slag is lighter, it flows out next and is poured into another ladle or a special slag pot. Next, the liquid ferroalloy is poured into large, flat molds, similar to giant frying pans, made of cast iron or lined with sand. After the fiery river of ferroalloy has filled the cast iron molds, a period of deceptive calm begins. The liquid metal cools and solidifies, turning into huge heavy plates or cakes. This is not the quiet, peaceful cooling of a pie on a windowsill. The rapidly cooling surface of the plate is covered with a bizarre network of crystalline patterns, and from the inside, a powerful heat continues to emanate for a long time, distorting the air above it. From time to time, a sharp, gunshot-like crack is heard. These are the internal stresses that arise during crystallization finding their release. Each such cake is a monolithic piece of metal weighing several tons, concentrated power, frozen in its primordial form. But this is not the final product. It's just a semi-finished product. In this form, the ferroalloy is completely inconvenient for use in steel mills. Imagine a chef who needs to add exactly 5 grams of spices to a recipe, but all he has is a 5-kilogram stone block of those spices. It's the same for a metallurgist. He needs to add a precisely measured amount of manganese or silicon to a ladle of liquid steel to achieve the desired properties. It is impossible to chip off a piece by eye from a multi-ton plate. A product is needed that can be accurately weighed and evenly distributed in the melt. Therefore, these solidified plates are sent to the final, most brutal stage, crushing. The plates are lifted into the air by powerful cranes and fed into the maw of a real mechanical monster, a jaw crusher. This is a machine that inspires awe. 2 massive grooved steel plates, or jaws, form a V-shaped space. One of them is stationary, while the other makes slow but relentless movements, like the jaw of a prehistoric monster. When a metal cake falls into this maw, a deafening crushing grind is heard, from which the ground vibrates. With a colossal force, measured in hundreds of tons, the steel fangs bite into the ferroalloy. The first crack, then another, and now the monolithic plate is breaking into large blocks, which fall deeper under their own weight, where the jaws come even closer, again and again breaking them into smaller and smaller pieces. But that's not all. The stream of crushed metal is poured onto a conveyor and heads to the next stage, sorting. It falls onto giant vibrating screens, multi-tiered sieves that continuously shake and rattle. This is a real metal waterfall, where pieces of ferroalloy dance and bounce to the accompaniment of a deafening roar. On the top tier, the largest pieces remain, which are often sent back for recrushing. Smaller pieces fall through to the lower tiers with finer openings. Thus, the entire stream is divided into clearly defined size groups, or fractions, from large, fist-sized pieces to small, gravel-like ones. This separation is extremely important, as different steel-making processes require different sizes of ferroalloy for optimal dissolution in liquid steel. And here it is, the final result, unremarkable in appearance, gray, silvery, or black stones of various sizes. They look like ordinary construction debris, but in fact, each such stone is a concentrated code of strength, a chemical key to creating outstanding materials. Each of them is a carrier of the energy spent on its extraction and smelting. In this form, they are poured into huge, strong bags, so-called big bags, marked and sent to metallurgical plants around the world. And there, added at the right moment into a boiling cauldron of liquid steel, they will fulfill their main mission. They will undergo their final baptism by fire, dissolve without a trace, and forever transform ordinary iron into an outstanding material, capable of becoming the foundation for a skyscraper that pierces the clouds, or a reliable bridge that connects continents. Every year, over 2 billion tons of trash are generated worldwide. It's as if every inhabitant of the planet threw away 5 kilograms of waste every day. But did you know that this trash is now not just a problem, but a goldmine for a new industry? In workshops where just yesterday, dirt and danger reigned, today high-tech hunters are at work. Robots that see more than the human eye and can sort in seconds what humans struggled with for years. And this is just the beginning. If you watch until the end, you'll find out how one teenager's idea changed the fate of the entire ocean. The waste management sector is undergoing a technological revolution thanks to the implementation of artificial intelligence and robotics. At modern recycling plants, robotic manipulators, controlled by complex algorithms, sort waste with incredible speed and accuracy. Computer vision systems identify different types of materials, such as plastic, glass, paper, and metals, which significantly increases the recycling rate and reduces the amount of trash that ends up in landfills. On a wide conveyor belt, a continuous, chaotic stream of what we've thrown away. Plastic bottles, crumpled cardboard boxes, aluminum cans, milk cartons, glass bottles. To the human eye, it's just trash. Almost impossible to sort through. And for a human worker, it's hard, dirty, and dangerous work. And so, above this stream, like a relentless hunter, it hovers, the sorting robot. This isn't a humanoid android from science fiction movies, but rather a high-tech industrial manipulator, similar to a giant steel arm mounted above the conveyor. But all its magic is inside. Its eyes are not just cameras. They are complex multispectral sensors that see the world differently than we do. They can distinguish materials by how they reflect light, analyze their chemical structure, and shape in a fraction of a second. The heart and brain of the system is artificial intelligence. Before getting on the job, this AI underwent intensive training. It was shown millions of images of different types of waste, just like you would show a child a million photos of apples until they learned to recognize them flawlessly. In the same way, the robot learned to identify PET plastic, used for beverage bottles, HDPE, a denser plastic for canisters and bottles, paper, cardboard, various types of metals, and glass. And so the action begins. The conveyor is moving. The camera continuously scans the stream. The AI analyzes the images in real time. Target identified. Aluminum can. It sends a signal, and the steel manipulator makes a lightning-fast, almost imperceptible to the eye, move. A pneumatic suction cup, or a mechanical gripper, gently but firmly grabs the can, lifts it above the stream, and with a precise movement, drops it into the corresponding container on the side. Before the can has even landed, the robot's eye has already spotted a water bottle, and the arm flies to a new target. Speed? A human can't compare. Some models can perform 100 manipulations per minute. That's more than 1 grab per second. Accuracy. The robot doesn't get tired, doesn't get distracted, and doesn't make mistakes due to inattention. Its sorting efficiency reaches over 95%, which significantly improves the quality of secondary raw materials. It can work around the clock, stopping only for maintenance. This isn't just a replacement for manual labor. It's a quantum leap that makes recycling much more efficient and economically viable, turning the problem of trash into a real resource for a new industry. The sorted materials, piles of hard plastic, bulky metal structures, wooden pallets, lie in separate mountains. They have been sorted, but are still too large, too awkward to be given a new life. This is where the true heavyweight of the recycling industry comes onto the scene, a machine whose job is controlled, brutal force. This is a rotary shredder. Externally, it looks like a huge steel box, but its heart is a massive, heavy rotor, studded with rows of extremely strong, hardened steel teeth or hammers. This is not just a machine. It's an insatiable beast, powered by a powerful motor that provides colossal torque. Its task is simple, but critically important: to shred. When material is fed into its huge maw by a conveyor or a manipulator, be it an old car bumper or a whole pile of plastic barrels, a spectacle of unstoppable power begins. As it rotates, the rotor's teeth grab the objects, pull them inside, and with a deafening roar and grinding, tear them into pieces. There's no room for delicacy here. Hard plastic cracks, metal bends and tears, wood turns into splinters. This process is a demonstration of pure physical force, aimed at one goal: size reduction. But why this destruction? It's not senseless annihilation, but a key preparatory stage. First, the shredded materials become uniform in size, making them much more convenient for transportation and further processing. Second, it's a process of liberation. The shredder breaks down complex objects into simpler components, making it easier to separate different materials from each other in subsequent stages. And most importantly, it creates the ideal raw material for further recycling. A pile of small plastic pieces is much easier to melt in a granulator than whole bumpers. Huge accumulations of plastic in the world's oceans, such as the Great Pacific Garbage Patch, are one of the most acute environmental problems of our time. By the way, do you believe that this patch doesn't exist? However, thanks to bold engineering solutions, there is hope for cleaning up the marine spaces. The problem is so gigantic that it seems unsolvable. How can you clean up something the size of several countries? Most people just threw up their hands, but not Dutch teenager Boyan Slat. In his mind, a bold yet brilliantly simple idea was born, which grew into one of the most ambitious environmental projects of our time: the ocean cleanup. The principle of the project is not to chase plastic all over the ocean, but to make the ocean itself deliver the garbage to a trap. For this, giant U-shaped barriers were created. This is not just a net, but a complex engineering structure consisting of a long, floating boom on the surface that prevents plastic from floating over it, and a deep mesh skirt underwater that traps the garbage, but allows marine life to swim freely underneath. The most interesting thing is how this system moves. It has no engines. It passively drifts, carried by the same forces that move the plastic: wind, waves, and ocean currents. But thanks to its design and a large sail above the water, the system moves slightly faster than the plastic passively drifting in the water. This creates a small but constant difference in speed. The barrier, like a giant shepherd, slowly but relentlessly gathers its plastic flock inside its U-shaped arch. The path to success was not easy. The first prototypes broke under the pressure of ocean storms, and unforeseen engineering problems arose. But after a series of trials, errors, and significant improvements, the system began to work effectively. Now, from time to time, special support vessels approach the filled barrier and, like giant garbage trucks, unload the collected tons of plastic. This plastic, from old fishing nets to tiny fragments, is brought to shore, where it is sorted and sent for recycling, closing the loop. Thus, an idea born in the mind of a young dreamer has turned into a real, working technology that offers hope for cleaning our oceans. Realizing that cleaning up the ocean without stopping the flow of trash entering it is like bailing water out of a leaking boat, the ocean cleanup team asked themselves a logical question: couldn't we just plug this leak? After all, research shows that the vast majority of plastic enters the world's oceans through just a small number of the most polluted rivers in the world. Thus, the Interceptor was born, a technology aimed at tackling the problem at its source. It looks like an elegant, futuristic catamaran, anchored in the middle of a river. It is completely autonomous and runs on 100% solar power, thanks to the panels covering its upper part. Its design is thought out to the smallest detail to be as effective as possible and not to interfere with navigation. Every year, Over 300 million square meters of glass are tempered worldwide. That's like 9,000 football fields turned into transparent armor. But few people know what happens if you try to drill through such glass, or why a single air bubble can lead to an explosion. In this video, we will take you through a real fire, into a furnace where ordinary glass becomes almost indestructible. And at the very end, you'll learn one thing they never tell you in stores, but which could save your life. It all starts with the perfect candidate. You can't just take any piece of glass and throw it into the furnace. No, preparation here is the key to everything. A large sheet of ordinary raw glass, known as float glass, arrives at the production facility. And the first rule of the tempering club is, all modifications happen before the start. Need to cut the glass to a precise size? Do it now. Need to drill holes for fasteners or handles? You better do it now. Need to grind and polish the edges to a perfect smoothness? There's no better time than now. Why such strictness? Because after the glass has gone through the furnace, it becomes untouchable. Trying to drill or cut tempered glass is a guaranteed way to instantly turn it into a shower of a million small, blunt cubes. Its internal stress is so great that any surface disturbance leads to an explosive release of energy. So, each piece is carefully prepared, inspected for the slightest defects, microcracks, or air bubbles, which in the furnace can become the epicenter of a catastrophe. And then it is washed and dried to perfect cleanliness. When our glass recruit is ready, it heads to the main event, the tempering furnace. This is a long, low tunnel, red hot inside, with a series of ceramic rollers that form a moving track. The glass smoothly rolls onto these rollers and begins its journey into the very heart of the heat. The temperature inside reaches about 1,150 degrees Fahrenheit. This is hotter than most home ovens in self-cleaning mode. Inside, the glass begins to glow with an eerie orange-red light, like a piece of red-hot metal. It doesn't melt to a liquid state, but reaches its softening point. At this moment, its molecular structure becomes slightly plastic. All internal stresses that arose during production are relieved, and it becomes perfectly relaxed and ready for transformation. The glass slowly moves back and forth on the rollers to ensure absolutely uniform heating of every square inch. And now comes the moment of truth. The red-hot, softened sheet of glass rolls out of the hellish maw of the furnace and is immediately ambushed. From all sides, top and bottom, a barrage of cold air under high pressure hits it. This process is known as quenching, or tempering. Dozens of powerful nozzles with a deafening roar blast the glass surface. This sudden, extreme cooling is the key to the whole process. The outer surfaces of the glass instantly solidify, harden, and compress, forming a strong, hard outer layer. But inside, the glass still remains hot and plastic. Over the next few moments, the core of the glass also begins to cool, and, like any material, tries to contract. But it cannot do so freely, because it is already held by the cold, hard outer layers. As a result, an incredible internal struggle arises. The cooling hot core pulls the outer layers inward, creating a state of huge tension in the center of the glass, like a stretched string. In response, the outer layers are under an incredible force of compression. In essence, the glass turns into a stress sandwich. Two strongly compressed outer layers and a tense, stretched inner layer. It is this brilliant internal architecture of stresses that gives the glass its new superpowers. It looks the same, but now it is a completely different material in terms of its properties. Ordinary glass has a bending strength of about 6,000 pounds per square inch. Tempered glass easily withstands over 24,000 psi, making it 4 to 5 times stronger. But its main advantage is safety. When ordinary glass breaks, it forms long, sharp, dagger-like shards capable of causing serious injuries. When tempered glass finally reaches its breaking point, something completely different happens. All that colossal accumulated energy of compression and tension is released simultaneously across the entire sheet. This causes the glass not to crack, but to instantly shatter into thousands of small, pebble-like pieces with dull edges. This is the very same famous crumb you've seen on the side of the road after an accident. And it is this property that makes it mandatory for use in glass shower doors, side windows of cars, and glass facades. Thus, through precise control over fire and cold, an ordinary fragile material is transformed into a reliable and safe protective barrier that silently serves us in everyday life. The tempered glass market in the United States is a significant segment of the economy. According to various estimates, its volume in 2024 was between $19 billion, $700 million, and $32 billion, $4 million US. It is projected that by 2033, this market could reach $47 billion, demonstrating stable annual growth of over 4%. Tempered glass is one of the key products in the market, along with basic, laminated, and insulated glass. In the US, there are over 4,000 enterprises engaged in the production of glass products. Construction is the largest consumer of tempered glass. Last year, the construction sector accounted for almost 79% of the contract glazing market. It is used for facades, windows, partitions, shower enclosures, and doors. Demand is stimulated by strict building codes and the growing popularity of energy-efficient green buildings that require certification. The automotive industry is the second largest consumer, using tempered glass for side and rear windows, as well as sunroofs. The growth in automobile production, especially electric vehicles where lightweight construction is important, supports high demand. Last year, over 15.5 million vehicles were sold in the US. The consumer electronics segment is also growing rapidly. Tempered glass is used to protect the screens of smartphones, tablets, laptops, and other devices. It is also used to make refrigerator shelves, microwave and oven doors, as well as countertops and furniture elements. Well then, let's take a look inside the tempered glass testing laboratory. On a special stand, a test sample of glass is installed in a sturdy frame. Opposite it, suspended on a calibrated pendulum, hangs the main testing tool, a heavy bag similar to a boxing punching bag. But it's filled not with sand, but with 100 pounds of dense lead shot. The choice of lead shot is not accidental. It allows the bag to deform upon impact, simulating the soft contact of a human body, unlike the impact of a hard object like a hammer. The test has two main categories, differing in the force of the impact. For Category 1, which is applied to less risky areas, the bag is released from a height of 18 inches, creating an impact energy of 150 foot-pounds. For Category 2, intended for high-risk areas like glass doors, the drop height is 48 inches, which generates a much more powerful impact of 400 foot-pounds. And now, the moment of truth. The bag is released, it flies in an arc, and strikes the exact center of the glass sheet. If the glass does not break, it automatically passes the test. But for tempered glass, the most important thing is what happens when it does break. With a sharp, dull crack, the glass instantly shatters into hundreds, even thousands of small fragments. Now begins the most meticulous part of the job. A lab technician carefully collects all the fragments resulting from the shattering. His task is to find the 10 largest fragments that do not have their own cracks. This is important. Each of these 10 fragments must be intact. Then these 10 pieces of glass are placed on high-precision scales. The verdict is issued according to a simple rule. If the combined weight of the 10 largest fragments is less than or equal to the weight of 10 square inches of the original glass, the test is passed. If it is greater, the glass does not meet safety standards. Behind this seemingly complex rule lies simple logic. It ensures that when the glass shatters, it does not create large, heavy, and potentially dangerous fragments capable of causing deep cuts. This strict and standardized process guarantees that the glass surrounding us, in case of damage, will break into relatively safe crumbs, not into razor-sharp shards. Every year, over 50,000 tons of uranium are mined worldwide. But to get just a few grams of energy from it, you have to move mountains. It all starts in the desert, where the temperature reaches 100 degrees and ends in a reactor that powers New York. Here, centrifuges that spin faster than an airplane turbine, and substances that corrode metal in seconds. But the most interesting part is what even safety instructions don't talk about. Watch until the end, and you'll discover a secret that will change your perception of nuclear energy. It all begins in the dust. And that's not figuratively speaking. Uranium ore is mined in hot regions: Arizona, Wyoming, Texas, New Mexico. Sort of like cowboy landscapes, only instead of lassos, there are drilling rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is scorching, up to 100 degrees Fahrenheit in the shade, if you can find any. There are two ways of mining: open pit, where the top layer of soil is removed and the ore is pulled out by excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. And there's also the in situ leaching method. Pipes are driven into the ground, and special solutions are pumped in to wash out the uranium directly from the rock, and then it's pumped back out. All this ore, a grayish-brown rock, looks no different from ordinary stones. But in it, uranium-235 is only 0.7%. The rest is almost useless mass that doesn't work in a reactor. And to squeeze the needed drop of energy from it, you have to process hundreds of tons. That's why they say nuclear energy is quite a marathon. After mining, the ore is crushed, ground, and thrown into a chemical bath. Acid or alkaline solutions are added to extract the uranium, like coffee from a filter. Then, filtration, precipitation, drying at 500 degrees Fahrenheit. And at the output, yellowcake, a yellow powdery concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellowcake. It looks beautiful, mustard-colored, fluffy, like a spicy powder for barbecue. But God forbid you inhale or touch it. Alpha radiation, a long half-life, dangerous dust that penetrates the lungs and settles there forever. People work with it only in respirators, suits, behind 3 layers of glass protection. Yellowcake is packed into double-walled barrels, loaded onto trailers with an escort, and wrapped with radiation signs. And off it goes to the enrichment plant. It's from this poisonous dust that the journey begins, leading to the white light of a lamp over a kitchen table, or the electricity in the subway rushing under New York. Well then, yellowcake is here, in barrels, radioactive and dry as a desert wind. The next step, turning it into a gas. And not just any lavender-scented gas, but uranium hexafluoride, the very same from which the required isotope for reactors and more is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, and converted into uranium dioxide. And here the magic begins. Uranium dioxide is treated with fluorine in special reactors at a temperature of 1000 degrees Fahrenheit. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees Fahrenheit. That is, you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It is extremely toxic. It corrodes metals, destroys skin, and in humid air, it immediately turns into hydrogen fluoride and uranic acid. That is, a deadly cocktail. That's why all this is done in sealed, automated reactors that look more like devices from a villain's laboratory. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, monitoring the sensors. Any mistake, boom, or hiss, and you're already in a hazmat suit, scratching your heels on the way to the shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, barrels with engravings, a batch number, and a radioactive sign. Each one weighs under 14 tons. And so, mission accomplished. The dust is turned into gas, ready for the most interesting part: isotope enrichment. But don't rush to celebrate. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think spinning a washing machine is fast? You haven't seen nuclear centrifuges that do 70,000 revolutions per minute. That's 10 times faster than an airplane turbine. And all for one thing, to separate uranium isotopes. The fluorine-enriched uranium dioxide, that same poisonous gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms fly to the edge, while the lighter U-235 atoms stay closer to the center. A tiny, microscopic difference, 1% in mass, and all this explosive technology spins just for it. But one centrifuge is not enough, so they are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so cycle after cycle, until the U-235 content becomes at least 3 or 5%. This is the reactor standard. For weapons, of course, completely different routes are taken. They are classified and under strict international control. Okay, the gas is enriched, but in its gaseous state, it won't feed a reactor. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark gray color. This powder is pressed under a pressure of 20 tons into small cylindrical pellets with a diameter of 3/10 of an inch. They look almost cute. But each such pill is like a charge of energy equivalent to 17,000 cubic feet of natural gas. Next, the pellets are sintered in furnaces at almost 3,000 degrees Fahrenheit to make them strong, like porcelain. Then they are polished, ground. Perfect dimensions are important for a tight fit in the cladding. The pellets are placed in long metal tubes, fuel rods, usually made of a zirconium alloy, because it doesn't rust, doesn't react with water, and withstands insane radiation. Over 300 pellets are placed in each rod. The rods are hermetically welded and combined into modules, fuel assemblies. They look like a frame of several dozen tubes, assembled in a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly, testing for leaks, uniformity of filling, weld integrity, behavior under temperature. There are no trifles, because each of them can cost not just money, but lives. The finished fuel is packed in armored containers that can withstand impacts, fire, and falls from a height. Transportation is under guard on a special route with an escort, GPS, and mandatory. 2 seals, 3 codes, and a dosimeter on each side. Because even in its peaceful form, this is a dangerous thing that commands respect. After all this, what remains is depleted uranium hexafluoride. They call it tails. It's a mixture of isotopes where there's still a bit of uranium-235, but not much. These tails are stored in steel drums on special sites under supervision. But in the future, they can be reprocessed in new generation reactors, where everything will be squeezed out to the last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It is removed, carefully, with a robotic system, and moved to pools of water. The depth is over 20 feet. The water cools and shields the radiation because the fuel is still hot, physically and radioactively. There it rests for several years. Then, 2 paths, either long-term dry storage in concrete containers with double walls, or reprocessing. In other countries, because the US mostly stores rather than reprocesses. In dry storage, the cassettes stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This is not the end, but a new stage of life. Slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Every hour, over 3,000 miles of electrical cables are laid worldwide. But few people know that this involves gigantic metal spools, each one an engineering marvel weighing over 20 tons. Their diameter can reach 33 feet, and inside, up to 37 miles of wire capable of transmitting hundreds of thousands of volts. A half-inch error, and everything goes down the drain in losses. How are these steel giants created with precision down to 1/100th of an inch? And why can't any power transmission line exist without them? Watch, and you'll be amazed. This story begins with calculations. Before the first bolt touches the steel, a team of engineers dives into mathematical alchemy. Each spool for a high-voltage power transmission line is created for a specific type of cable, so there are no trifles here. Blueprints, models, and calculations come into play. It is necessary to consider the outer diameter of the cable, for example, 2 inches. Its weight, which can exceed 3 pounds per foot. Density, number of turns, winding angle, and even the insulation's coefficient of friction. On average, up to 6 miles of cable are wound onto one spool. That's almost 32,000 feet of heavy, multi-insulated wire that, under voltage, can carry hundreds of thousands of volts. An error of just half an inch in the spool's diameter, and the cable might start coiling incorrectly, shifting, compressing, overheating. In the worst case, it gets damaged even before installation. And that's tens of thousands of dollars in losses before even starting. Moreover, the core diameter of the spool can reach 5 or 6 feet, and the total diameter of the flanges up to 33 feet. The weight of the structure exceeds 40,000 pounds. That's like 2 large SUVs, screwed together and stood upright. And this entire mass has to rotate smoothly, without misalignment or vibrations. Are you impressed? Because I sure am. To avoid disasters, engineers add a coefficient of material expansion. As metal changes size when heated, consider transport weather conditions, and also the winding geometry, because even too steep a winding angle can damage the cable when it's unwound. When the drawings are approved, giant workshops come onto the scene, hangars the size of a football field. Here, metal flanges, cores, and frames appear. Most often, the spools are made of steel. It's steel that can withstand the weight of the cable and the loads during transport. For an average spool, more than 2 tons of steel are needed at the laying site. So, each giant spool for power transmission lines starts with cold metal, thick steel sheets that arrive at the factory as plates measuring 6 by 12 feet or more. Their thickness ranges from half an inch to 1 inch, and this steel is structural. Strong, tough, capable of withstanding high loads without cracking or deforming. First, the sheets are fed to plasma or laser cutting machines, which are programmed according to precise drawings. A giant plotter, emitting a hot beam, literally burns complex shapes into the metal. These machines operate with an accuracy of 1/100th of an inch. Such precision isn't for beauty's sake, it's critical. Because even the slightest error on one flange can cause the spool to lead the cable off-center during rotation. And that's a risk of misalignment, jamming, and failure during installation. The discs for the flanges are cut in pairs, identical rings 20 to 33 feet in diameter, with holes for connecting bolts. Technical slots and markings for future reinforcing elements are made on the surface right away. After cutting, they are processed by grinding machines. Burrs are removed, and they are prepared for welding. At the center of the future spool is the core, a large steel pipe that will serve as the drum for winding the cable. Usually, its diameter is from 5 to 8 feet, and its length up to 10 or 16 feet. The pipe is cut from thick wooled rolled stock and reinforced with stiffening ribs inside. These are thick steel strips that form a frame and prevent the pipe from sagging under the weight of the cable. After all the parts of the future spool are cut, the stage where every millimeter matters begins: welding and assembly. Here, metal geometry transitions from 2-dimensional to 3-dimensional. 2 giant flanges are attached to both sides of the core. A steel pipe that will hold tens of thousands of feet of heavy cable. The entire structure must withstand not only its own weight, but also dynamic loads during rotation and transport. Welding is done manually or automatically, depending on the size and complexity. Most often, submerged arc welding is used, which allows for creating dense, strong seams without voids. The joints are additionally ground, as any protrusion or unevenness can damage the cable during winding. Then, reinforcement. Stiffening ribs, which are thick steel plates placed inside the core and at the joints with the flanges, are added to the structure. They prevent deformation under pressure. To fix all the parts, bolts up to 1.5 inches in diameter are used, tightened with special hydraulic torque wrenches. One such bolt can withstand a load of tens of thousands of pounds. The finished spool is installed on a temporary axle and rotated. Engineers check the balance using a laser level, ensuring that during rotation, no part shifts even a quarter of an inch. If the structure wobbles, it's ground, adjusted, and sometimes parts of the elements are reassembled. And only after this is the spool considered ready for the final stage: anti-corrosion treatment, painting, and testing. The finished spool has just been removed from the rotating stand after welding. It's still warm, smells of metal and ozone, and its surface is covered with dark gray spots. That's scale. It looks like a thin crust, similar to coal dust, and remains after the metal comes into contact with high temperature. Along with it, small remnants of oil, dust from grinding, handprints. Painting in this state is a waste of time. The coating won't stick, it will peel off in the first few months. So first, mechanical cleaning takes place. The workshop buzzes with tools. Workers with stiff brushes on grinding machines go over the joints, flanges, and stiffening ribs. They remove rough irregularities, clean the seams of residual slag. But this is not enough. Next, a sandblasting unit comes into play. A large chamber, or just a separate section in the workshop. The spool is brought inside on a special platform. Then, the roar of a compressor and a stream of fine abrasive starts hitting the steel surface under high pressure. Sometimes quartz sand, sometimes steel balls. It sounds like a storm of hail hitting tin. The surface changes before your eyes. Where there was just dark mottling, now there is an even, matte gray metal with a slight roughness. If you run your finger over it, you feel not smooth, but slightly velvety to the touch. This is exactly what's needed, because this micro roughness significantly improves adhesion with the anti-corrosion primer. In chemistry, this is called the anchor profile effect. When the treatment is complete, the entire surface is blown with air, blowing out residual abrasive from corners and crevices. This is the perfect moment to apply an anti-corrosion primer, the first protective barrier between the metal and the environment. A worker in a mask and protective suit takes a sprayer with a thick gray liquid, a zinc-rich primer. With each press of the trigger, a thin, even mist comes out of the nozzle, settling on the surface. The zinc in the primer acts as a sacrificial metal. It is the first to react with moisture, saving the steel from corrosion. After a few minutes, the spool is already covered with a thin, almost invisible layer. It looks a little lighter, as if dusted. In a few hours, this primer will polymerize and form a chemically resistant film that is firmly bonded to the metal. It is this layer that takes the first hit from time, moisture, and temperatures. For export or harsh climatic zones, additional layers may be applied: marine varnish, hydrophobic films, or even heat-resistant coatings that can withstand heating up to 300 degrees Fahrenheit. When the coating dries, the spool is carefully inspected. Under ultraviolet light, all microcracks, bubbles, or gaps in the layer are visible. If there are doubts, an electric spark test is performed. A special probe glides over the surface, and a spark jumps only where the insulation is compromised. This ensures that every inch of metal is reliably protected and will withstand years of operation in any conditions. Every year, over 20 million metric tons of copper are mined worldwide. But only 1% of that massive amount makes it into the shape we see every day, as thin pipes that cool our homes, offices, and skyscrapers. This story begins in the giant mines of Chile, where excavators as tall as 5-story buildings dig up the ore from which a gleaming pipe is eventually born. From explosions in quarries to magma in furnaces. from thousands of degrees to surgical precision. How does a piece of mountain rock turn into an air conditioner? We're about to show you the whole journey, step by step. Deep underground, in the deserts of Chile, the steppes of Kazakhstan, and the mountainous regions of Australia, work is buzzing, slow, monotonous, but extremely important. Here, copper ore is extracted, the raw material from which thin, shiny pipes for air conditioners are later born. This process begins far from factory workshops, in giant quarries, where every explosion, every excavator bucket, is a step towards the metal that will cool rooms in skyscrapers and apartments. In Chile, which produces nearly a third of all the world's copper, there are giant open pit mines, for example, the famous Escondida. Here, mining machines as tall as a 5-story building slowly move down the terraces, scooping up rock from which only 1% of copper is extracted. Imagine, to get 1 ton of metal, you need to crush over 100 tons of rock. After extraction, the ore goes to crushers, huge machines that turn rock into pieces the size of a walnut. Then, even smaller, down to sand. This sand goes to flotation plants. There, using water, air, and chemical reagents, copper floats to the surface as foam, which is skimmed off, dried, and sent for smelting. All of this is heavy, energy-intensive work, but without it, there would be no pipes, no air conditioners. From the first blast in the quarry to the thin pipe in an office, the journey takes months, covering thousands of miles. And each stage is a story of its own. Raw ore isn't transported to the factory where copper pipes for air conditioners are made. That would be too bulky and inefficient. Instead, after concentration and primary processing, it's turned into a more concentrated, transportable product. Depending on the supply chain, the factory might smelt the concentrate or mat themselves, producing pure copper if they have melting facilities. Or they might purchase cathode copper in the form of plates and then form blanks for pipes from it. Shiny rectangular plates. These are copper cathodes, weighing up to 200 pounds each. They are stacked on pallets and brought to the factory in incredibly long trucks. This is almost pure copper, over 99.9%, and it will become the heart of future pipes. But first, it will turn into red-hot ingots. Cathodes are removed from pallets and inspected, checking for cracks, oxidation, or dirt. Next, they need to be cut for remelting, as they are incredibly large. The cathodes are placed one after another on a hydraulic table, and a heavy-bladed press descends from above, literally chopping the copper in half. The sound is a dull metallic thud, almost like a gunshot, quick and precise. When more complex shapes or smaller volume are needed, a bandsaw with carbide teeth is used. It slowly but steadily cuts the copper, like wood, only with water cooling, because the metal heats up. If the copper needs to be cut at the melting location, a plasma cutter or an acetylene torch is sometimes used, a stream of burning gas that melts the metal along the cut line. But for cathodes, this is less common. It's too expensive a technology. All operations are usually automated. Cathodes are brought by a crane or forklift, loaded onto a conveyor belt, and everything moves down the line. The cut pieces are immediately fed into the furnace. The operator only ensures that everything moves smoothly and without jams. The cut pieces fall onto a metal roller or chain conveyor. There they lie flat, often in a single layer. If needed, they are separated by special pushers to prevent them from sticking together or getting stuck. This conveyor works slowly but powerfully. The task is to continuously feed copper into the furnace without creating bottlenecks or downtime. After melting, fluxes are added to the molten metal, substances that collect impurities and scale, help keep the copper clean and shiny, and reduce slag formation. The fluxes float to the surface as a dark film, which is scooped up with a mechanical skimmer and discarded. As soon as all the copper has melted and become a uniform, shiny mass, the temperature is equalized and the furnace opens from the bottom or tilts, pouring the metal into casting molds. The molds resemble long, rectangular boxes with thick walls, made of strong steel capable of withstanding intense heat. The furnace is tilted, or a valve is opened, and the hot molten copper begins to flow along a special channel, like a bright orange river of magma. This channel leads to the mold, which stands ready to receive the metal. The mold is cooled by water or air, so the copper entering inside begins to solidify quickly. Immediately after pouring, the mold is often lightly tapped or vibrated a bit. This helps air bubbles and voids escape from the molten metal, ensuring the ingot is strong and without defects. The mold stands on a special platform that sometimes moves or tilts slightly, helping the metal distribute evenly. The hot steam rising above the mold resembles volcanic smoke. Workers in special protective clothing observe the process, ready to intervene if something goes wrong. As soon as the copper in the mold cools and solidifies, the mold is opened and a long, shiny ingot comes out, a large piece of copper, ready for further processing. These ingots can weigh hundreds of pounds and look like metal bars with a smooth, shiny surface. The ingot that came out of the mold first undergoes quality control, checking its weight, shape, and absence of cracks or defects. Then it is heated to a certain temperature to make the copper softer and more pliable for further processing. Next, the ingot enters a large rolling mill, where it is gradually rolled between rollers, stretching and making it thinner. Rolling happens several times to make the ingot longer, thinner, and more uniform in thickness. After rolling, the metal undergoes special forming. It is turned from a flat strip into a cylinder, which is then welded along the seam or blown into a pipe shape. This process is very precise. The diameter and wall thickness are regulated with great accuracy so that the tubes can withstand pressure and don't burst. After forming, the copper tubes are still hot, almost like a freshly baked bun. To prevent them from deforming and to keep their perfect shape, they are cooled quickly. For this, the tubes are passed through long pools of cold water or special cooling baths. Water sprays from different sides, flowing around the metal, and it cools down instantly. Then, the most interesting part begins, checking the dimensions. The tubes pass through special calibrating devices. This can be a set of rings or sensors that measure the pipe. Each ring corresponds to the exact inner or outer diameter. If the tube passes through the ring without problems, the size is normal. If not, an automatic sensor signals, and the operator stops the process. If the pipe meets the standards, it is sent further, for cutting or packaging. If not, it is returned for rework or recycled, to prevent defective products from reaching the customer. After the copper tubes have undergone forming, cooling, and calibration, they proceed to the next important stage, cutting into standard or ordered lengths. This process is very important, as the quality and ease of installing the pipes in air conditioners depend on the accuracy of cutting. The tubes are usually supplied in the form of long straight sections or coiled into bundles. First, they are uncoiled or fed along a conveyor to a special automatic cutting machine. This machine is equipped with a powerful cutting disc or saw that rotates at high speed. The operator sets the precise parameters for the cutting length, for example, 10 feet. The tube is fed forward, and the machine precisely cuts off a piece of the required length. The moment the cutting disc touches the copper, sparks fly, and the metal almost hisses and smoothly separates into two parts. The movement of the disc is very fast and smooth, so the cut is even and clean, without burrs or cracks. The finished tube sections are packaged into bundles or boxes, often wrapped with tape for easy transport. Each package is marked, indicating the tube dimensions, wall thickness, and production date.